Hey guys, welcome to my final project presentation for my project Performance Analysis of OFDM Systems, done for the course Wireless Communications under Dr. Dapeng Wu at the University of Florida. So the first question is, what is an OFDM system? So OFDM stands for Orthogonal Frequency Division Multiplexing, and it is a multiplexing technique which helps in the modulation of digital data onto multiple carrier frequencies. So OFDM has a variety of uses in real-life applications, including wireless networks and 4G. So in simpler terms, orthogonal frequency division multiplexing is a summation of all the subcarriers that have been modulated with message signals. The modulation technique that we'll be using in this project is BPSK. Unlike the other multiplexing techniques, OFDM does not need the subcarriers to have a minimum spacing or guard bands between each other. Now, this is the advantage of OFDM, and this is actually done by having the subcarriers orthogonal to each other. Now, for two signals to be orthogonal to each other, the minimum frequency difference needs to be the reciprocal of the symbol period. So the subcarrier frequencies will be 1 by t, 2 by t, 3 by t, so that they are all orthogonal to each other. Now the modulation technique that we are using in this project is BPSK. Now in BPSK, the changes in phases of the carrier signals represents the binary input. That is, when theta is equal to 0, it represents a 1, and when theta is equal to 180, it represents a binary 0. Now, why should we use BPSK and what are the advantages? So the advantage of using BPSK is that it's pretty robust, and it can be used in communication systems that use communications over large distances, and it is also power efficient. Now, moving on. So in order to make the OFDM system more reliable, we include a cyclic prefix to it. So what is a cyclic prefix? The cyclic prefix acts as a buffer region or guard interval to protect the OFDM signals from ISI, that is intersymbol interference. Now it actually occurs between each symbol that is transmitted. So it actually repeats the end of the symbol so that the linear convolution of a frequency selective multipath channel can be modeled as a circular convolution, which in turn may transform to the frequency domain via a DFT. Now this approach accommodates simple frequency domain processing as well, such as channel estimation and equalization. Now moving on to the channel types. So there are primarily two channel types that have been used for performance analysis in this project. The first one is additive white Gaussian noise channel, and the second one is Rayleigh multipath fading channel. Now let's talk about the channels in detail now. Now for the first one, that's Rayleigh multipath fading channel, it is actually a statistical model for the effect of a propagation environment on a radio signal such as that used by wireless devices. So in simpler terms, it is a good model to be used when we want to simulate an environment, a normal natural environment for your wireless communication system. So in the statistic model, we would be able to see that the phase difference comes down to a value of 2 pi fc into the delay. So when the phase of each path can change by 2 pi radians when the delay changes by 1 by fc. So when the delay is 1 by fc, it cancels out with the fc term which is already present, and hence the phase would become 2 pi radians. So when the value of fc is quite large, then relative small motions in the mediums can cause a lot of change in the 2 pi radians. So it is actually reasonable to assume that the phase is uniformly distributed between 0 and 2 pi radians, and the phases of each path are independent. Now, by central limit theorem, when there are a lot of paths, then the paths can be individually treated as circularly symmetric complex Gaussian random variable with time being the variable. Hence, the random variable that obviously as mentioned that we'll be using is Gaussian. Now, the bit error rate, the theoretical bit error rate, is given by this expression, and it is dependent on EB by N naught ratio. So, in order to simulate this Rayleigh multipath fading channel, we have used the IEEE standards, and hence the FFT size for the OFDM is 64. The number of subcarriers is 52. Sampling frequency is 20, and so on and so forth. The cyclic prefix duration is 0.8 microseconds, and the total symbol duration is 4 microseconds. These are all the IEEE specifications for an OFDM system. Moving on to the second type of channel that has been used in this performance analysis is the additive white Gaussian noise. In this, the additive white Gaussian noise is what corrupts the transmitted signal. So when this noise is added to it, it actually means that we have added a flat noise spectrum, and the noise values will actually follow the Gaussian probability distribution function. Now let us assume that the transmitted signal be x1 or x0, which corresponds to us transmitting a 1 or a 0, then the probability of error when x1 and x0 are going to be the same. That is what we assume, and that's actually true as well. So using the law of total probability, we'd be able to say that the bit error ratio theoretical would be equal to this expression, and when it is factored down, we get into a final expression where the bit error rate theoretical is actually dependent upon the complementary error function and the EB by N naught ratio. So this system was actually simulated in MATLAB, and this is the MATLAB code for the Rayleigh multipath channel fading channel, and this is the MATLAB code for the additive white Gaussian noise channel. Now let's simulate the Rayleigh multipath channel first. So here is the result for the multipath channel. As you can see that the simulated values as well as the theoretical values do match to a good extent. Obviously we do have these points that don't fit the line for that instance. So this is for the Rayleigh multipath channel, and for the additive white Gaussian noise, even here we could see that it does fit in the sense that the values that have been used in the simulation and the theoretical values match. Hence we could say that the simulations were successful. Now let's see this. Let's evaluate these things, and let us analyze the performance. So if we look at channel 1 and channel 2 being additive white Gaussian and channel 1 being the Rayleigh, we could see that the BER is more when compared to for channel 2. So we'll be able to see that the additive white Gaussian noise has actually performed better when compared to the Rayleigh multipath fading channel. But then we could say that the Rayleigh fading channel is more of a better simulation to perform on a wireless communication in order to compare it with natural surroundings. So to summarize and to conclude, an OFDM system with different types of channels was simulated and analyzed successfully. Channel 1 is the AWGN channel, in which the additive white Gaussian noise is added to the signal after transmission. And the second channel that was used was a Rayleigh multipath fading channel, which is a model that effectively simulates a natural environment in wireless communications. In this channel, the fading occurs due to multiple paths available, and this also gives rise to attenuation and delay. The OFDM systems were added with a cyclic prefix to improve reliability, and in order to determine the performance, the BER versus EB by N0 values were plotted for the channels. The simulation outputs were quite similar to the expected theoretical outputs, and from the plots it was determined that additive white Gaussian noise channel has better performance when compared to the Rayleigh multipath fading channel. That's it for this project. Thank you so much for listening.